Hello everyone, and welcome to day 2 of the applications of derivatives. Last lesson we looked at how to find maximum minimums with the first derivative. Second derivative gave us concavity, and so we're going to look more into that today and how to use it given a function, and then more specifically given the first derivative with a graph, what can we tell? So a little review from last lesson. Find the maximum value for the function f of x equals 8x minus x squared. So take the first derivative, and then to find a maximum or minimum, you're going to take the first derivative, set it equal to 0, and so we know that implies 8 minus 2x equals 0, and move the 8 over, divide by negative 2, we're going to get x equals 4. With that, we do a number line. This is all review from last class, just in case you forgot. Plug 4 into the derivative. So plug 0 in first, that's a plus. Plug in 5, you're going to get a negative. And so increasing, decreasing. So we know that there's a relative maximum at x equals 4. If we wanted to find the y value, in case we did, you would say f4 equals 8 times 4 minus 4 squared, 32 minus 16, and we're going to get 16. So the actual point at which the relative maximum occurs is 416. And we know that this is true because this is a quadratic facing down with roots at 8 and 0. This is 8 and that's 0. We know that the maximum in a very poorly drawn graph, but a maximum would occur then at 16, and smack dab in the middle between 0 and 8 is 4. This is a continuous function. It never ends, and so therefore there is no minimum value, especially absolutely no relative minimum value. But if you look at the next question, it says find the absolute minimum and maximum. The absolute. Now, absolute means that it can include the endpoint. Absolute can include an endpoint. Note that an endpoint is not infinity. Okay? The endpoint is not infinity. An absolute minimum or maximum can occur over a specified interval where there is an endpoint. Notice that these are closed brackets. If they were open, you could not find an absolute at an endpoint. So if we want to do this, we would say f prime of x equals 3x squared. And so f prime of x equals 0, which implies that x equals 0. So we know that there is a critical point at x equals 0. And so what we are going to do, since these are endpoints, you're going to test f of negative 3, f of 0, and f of 1. This is an endpoint. This is an endpoint we test. This is a critical point, so we test that. We plug back in. Negative 3 cubed is negative 27. 0 cubed is 0. And 1 cubed is 1. So we have an absolute min at x equals negative 3. And the value is negative 27. And the absolute max at x equals 1. And the value is 1. We just know that by looking at it. If there had been 2 critical points, you would have tested both critical points. But again, why is this? If you look at this, here is your absolute minimum, here is your absolute maximum. It doesn't matter if there had been a local min or max here, it doesn't matter. It's just looking for the absolute. Now, if a graph had, we'll say looks like this, this would be the absolute min, this would be the absolute max, this would be nothing but an endpoint. So we're only looking for the highest and lowest point. It just depends on whether that's a relative min or max or an endpoint. So there's your review of what we did last class. And a little more here. A first derivative, we know that you can do increasing, decreasing. gives you critical points. This is by setting the derivative equal to 0, or what else, guys? Or when f prime of x does not exist. Make sure you remember that too. Maximum and minimums occur from doing the slope. This would be positive, negative, positive. So max here and min here. They're relatives. If you wanted to include that, they're relative. Min and maxes. And then second derivative tells us concavity and points of inflection. That's when the second derivative is equal to 0. So if we look at the second page, we are given, make sure we read, the first derivative. That's what this entire lesson is about. The first derivative, we're given the graph of it. We need to figure out what we can tell from the first derivative graph about the original graph. So we need to state the intervals of increasing, decreasing concavity, max and min, critical points of the original function. So if we look at all this, notice that a graph, let's start with this, f of x is increasing when what? F prime of x is greater than 0. Decreasing when f prime of x is less than 0. Well, this is the derivative. We are above the x-axis here and here. We are below the x-axis, so it's negative, less than 0, down here. So we are increasing from here to here and here to here. And we're decreasing when we are below the x-axis. So we can go right here, increasing from 0 to 3, or 1, 2, 3, 4, 5, 6, 7, 7 to 10. And we're decreasing in between there, 3 to 7. Remember that first increase and decreasing is closed intervals unless otherwise specified. The critical points, well, we know, we look back up here, critical points occur when f prime of x equals 0. Well, these are the x-intercepts. X-intercepts here and there. So x equals 3 and x equals 7. And then we can use this information to create a number line. Our critical points are 3 and 7. We know it's above the x-axis from 0 to 3, below the x-axis from 3 to 7, and above the x-axis from 7 to 10. And therefore we can say whether we're increasing or decreasing. So we have a maximum at x equals 3 and a minimum at x equals 7. And so therefore we've just done all of that just from looking at the graph. Now we do not know the actual value. We don't care, it's just the x value that we're looking at. We cannot tell the actual y value, so please note that there is no specific value for the max. Before we move on to the concavity portion, most people struggle with the idea of how to find information about the second derivative based on the first derivative graph. So if you get it, pause this, move on, or fast forward and move on. If you don't, this is what we're going to look at now. So all of this should look familiar. Pause this and make sure that it does. If you have any questions with this, you need to come see me after school. You are able to tell me information based on the first derivative graph, whether it was increasing, decreasing, maximum, minimum, or critical points. But what we struggle with is, given the first derivative graph, what do we know about the second derivative graph? Well, all we need to do here is kind of flip-flop. So this now becomes f prime of x, and this now becomes f double prime of x. If I give you the derivative, the first, if we think about it as the first derivative, that is the second derivative. So given the fact that we're given f of x, where f prime of x is increasing, we know that the second derivative would be what we think of as the first derivative graph. So if the first derivative is increasing, then the second derivative is concave up. If the original, in this case the first derivative graph, is decreasing, then we know that it is concave down. And if the first derivative graph has a max or min, then we know that the second derivative is equal to 0, which means it's a point of inflection. So basically all we're doing here is taking this original that we are given, making believe that it's, or saying it's the first derivative graph, and then basically plugging all of those in as the second derivative. So, again, if it was the original graph and it was increasing, we would know that the first derivative graph was, the first derivative is greater than 0. If it was the original graph was decreasing, the first derivative is less than 0. If there's a maximum or minimum, we know the first derivative equals 0. Now just shift that. If the derivative has any of those, then we know all of this right down here. So, knowing that, we are given the first derivative graph. Therefore, where is the first derivative graph increasing? If we're increasing, we know that's where it is concave up. First derivative graph, concave up. Where is it increasing? It's increasing from 5 to 10. Therefore, it is concave up from 5 to 10. We always use open brackets. Where is it decreasing? Decreasing from 0 to 5. That is where it's concave down. It's where the second derivative is less than 0. This is where the second derivative is greater than 0. And then where is the maximum or minimum? But at x equals 5, that is where the point of inflection is. So hopefully that chart helped a little more. Please pause this and look at the next page. Try to mark it up, and then when you unpause it, I will have the answer for you. So here's the answer to page 3. Notice that I kind of did something different here. I want to show you multiple ways. I know it's increasing when it's above the x-axis, so I did a bracket, f prime of x is greater than 0. Critical points occur when f prime of x equals 0, so it's at the x-axis, and decreasing any time below it. And so you can see the answers here. Remember that this is f prime of x, and therefore that's why we're looking to see where it's above or below the x-axis. It is the first derivative graph. Critical points, maximum and minimum, comes from the number line right here. And then, again, where is concave up? This is when the first derivative graph is increasing, and this is where the first derivative graph is decreasing. Again, if you need to, please scroll back and look at that chart. And this is when the first derivative graph has a max or a min. So again, I would like you to pause this and look at the very last page and try that. Again, I will have the answers for you when you unpause it. And so to end off the lesson, here is the answer to page 4 problem. Hopefully, after getting through 2 on your own, it starts to make more sense. If you have any questions, please come in and see me before class. Enjoy the day.